Welcome to Texas State University's Chemistry 2330 Introduction to Organic Chemistry. I'm your guide, Dr. David Irvin. We will conclude Chapter 6 with Part 4, Optical Activity. So, up to now, we were kind of defining what chiral things were and how they can be identified as either pairs of enantiomers or sets of diastereomers, okay? So, we're going to change gears a little bit and tell you what we call optical activity. This is how we know that we have chiral compounds, okay? So what we can see is that chiral compounds actually rotate light in such a way that we can measure that this is happening. So let's talk about that for a minute. Ordinary light has light waves vibrating in all different directions, okay? So a light wave has a component that goes up and down like this, and so it has a particular plane in which it's propagated, okay? So just regular light is not ordered. Those planes can go in any direction possible, and so what we're looking at is that we have all those different directions of light all the time, okay? So, but what we can do is we can actually put what we call a polarizer, meaning that only light that is aligned with each other can go through that filter. And so that now we have all of our light going in the same plane parallel to each other, okay? So we call this plane polarized light because they're all going in the same plane, okay? Then we have a device, what we call a polarimeter. We can actually measure where that plane is. So if we start with it in this position here, we can actually rotate the filter to see whether or not it has tilted off of where it is, okay? So by definition, something that is optically active is a compound that will rotate the light from going in this direction as it comes into the solution to some other plane when it comes out of the solution. If it rotates this light, if it changes this plane, we call that to be optically active, okay? So we're actually seeing that it has changed the rotation of light. So the device itself starts out with something like this. We have a light source that generates light, and when it generates that light, all those different planes are going in all the different directions. And then we filter that light such that they're all going in the same direction. That wave is all coming in that one plane right here. And then we fill the sample tube with our compound here. And every time that light interacts with that molecule that is optically active, it's going to rotate that light a little bit, okay? And when it rotates that light a little bit, if we left our filter exactly where it was when it started, we wouldn't see the full intensity of light. Some of that light would have been rotated out of plane, and therefore it is being blocked. So by rotating this filter until we get the maximum amount of light achieved, the maximum at that point, that means that most of the light has been rotated in that direction. And by measuring that degree difference, we've actually measured how much that light was rotated over the path of the sample here. So we have a couple new definitions. When we have a compound that rotates light clockwise in our polarimeter device, we call that dextrorotatory, or correctly, clockwise rotation, okay? Dextrorotatory. It's a lot of times it's used as a compound, we'll see a D, or dextrorotatory, okay? Now, if the light, instead of being rotated clockwise, is rotated counterclockwise, it actually turns out to be called levorotatory, or counterclockwise rotating, okay? We can also do what we call specific rotation. Specific rotation allows you to compare numbers from different laboratories by observing the rotation in exactly the same way in different places. So when we do that, we have a standard procedure we use. We use an optically active substance in a specific concentration, typically 1 gram per milliliter in a solution. And we have the tube is exactly 10 milliliters long, okay? Now, so that way it is calibrated for a concentration and a distance. And so when we look at this here, we can actually compare numbers from one lab to the other. So in the case of this compound here, S2-butanol, it actually rotates the light in a clockwise fashion, and therefore we get this plus sign here. So dextrorotatory is also a plus sign here. Levorotatory is the minus sign here, L and D. Okay. So in this case here, our specific rotation denoted by the alpha is, and again in these brackets here, is telling us that it's the light source we're using is a sodium D-line light. It's measured at 25 degrees, and it rotates the light clockwise 13.52 degrees. Okay. Now that means if this isomer, pure enantiomer, rotates the light in one direction by a certain number of degrees, that means the pure isomer of the opposite isomer should rotate it exactly that same number of degrees in the opposite direction. And this is found to be true. So the R derivative is levorotatory and will rotate it exactly 13.52 degrees in the opposite direction of the S isomer. Okay, so that's how we get to the dextrorotatory, which is clockwise, levorotatory, counterclockwise, in specific rotation, so we can compare that measurement from lab to lab to lab. Now, this is, except for some inorganic salts, and a few of the lower molecular systems, a lot of the materials are chiral. Most of the biological systems are optically active, but only one of the isomers is actually used in nature, okay? So most of the time, because they're created with enzymes and such, almost always there's only one of the stereoisomers that's typically found. And one of the more common ones that's found in biological systems is the dextrorotatory, okay? The reason for this is enzymes, or protein biocatalysts. They specifically rotate and fit things into one possible way, and being that the enzyme can only fit the chemical in one way, it only produces one isomer. Okay, therefore enzymes are very specific about making a specific isomer, even though of the 200 or so possible stereoisomers available to it, it only makes one. Okay, and the reason this works is because if you think about the enzyme as this very complex device, but it has specific pockets where different functional groups can fit in a certain way. And therefore, only the one isomer of the material can fit in that pocket because, remember, it's a non-superimposable mirror image. Therefore, the other isomer does not fit in the pocket. And therefore, the one isomer will fit in the pocket and will become enzymatically active. Okay? Because of this, many different of our prescription drugs, only one isomer is actually found in the device because only one is active as a pain reliever. For example, in the case of ibuprofen, the optical active version is the S derivative and not the biologically active species is the S derivative, not the R derivative of the material. It doesn't do anything to reduce pain or fever. In fact, if you go to something like naproxen, which is a derivative thereof, which is also a pain reliever, only the S isomer actually is the pain reliever. The R isomer is actually a liver toxin and is very bad for you. So when you get your material from the pharmaceutical company, they make sure that there is almost no R in there as the liver toxin, and all of the material is the active S derivative. Okay, so if we have an equal mixture of the two different enantiomers, we have what we call a racemic mixture. What this means is that half of the molecules are R, half of the molecules are S, which means half of the molecules are going to rotate it in one direction, half of the molecules are going to rotate it back in the other direction. Therefore, you end up with a net activity of 0. Okay, so a racemic mixture is equal moles of the two enantiomers. And we're going to see this again when we start doing reactions in chapter 7. Okay, now there is a way to separate these racemic mixtures into their different enantiomers, and this is called resolution. And typically we do this in a couple different ways. We use enzymes or salts to create a derivative that is active to a specific enzyme, and therefore only the S derivative of the naproxen here will react to clip off this group here, giving it the free carboxylic acid. The R derivative here of this ester does not affected by that, and therefore stays as the ester and stays in solution. This one can be extracted out of solution because it has this carboxylic acid. So by using an enzyme to selectively clip off one of the esters and not the other ester, we can actually separate the two optically active reagents from each other, from the pain-killing derivative versus the liver-killing derivative, which we don't want. So this concludes our chapter 6 on chiral compounds. Again, the most important things is chiral compounds have 4 different functional groups. They are identified as R and S. The different derivatives are available to us. If we have more than one stereocenter, we can have more than one set of enantiomers available, and those sets are called diastereomers.